Okay, I'm going to talk about statistical functionality for the OpenDP initiative. Just since we're all coming back from lunch, just the briefest of retrospectives. The sort of underlying theme here that stretch Salil's and Gary's and Merce's and Michael's and Marco's all talks was, how do you build a system that works for everybody? How do you build a system that works across a broad set of use cases that allows different kinds of researchers to pursue the research tangents they're going in, the definitions of privacy they're interested in, and allow that to be incorporated into this library? How do you allow system builders to utilize the same underlying system? As was said, in crypto, nobody rolls their own, right? So how do we build this carefully constructed library that works for everybody as a commons, and that we can all vet and that we can all reuse? And a theme that Gary touched on too is how do we make this of use to end users who are not crypto experts, who are not privacy experts, but understand privacy and address that in the real world consequences of their own data. Okay, so what I want to talk about is how do we make this library of maximum use to statistical analysts who are going to be using the products of the library, right? How do we build into the library, bake into the library things that will make the releases that we generate of maximum use for analysts down the road? And when I say analysts, I mean a broad swath of people. I'll keep calling them statisticians, but by that I really mean data scientists, people who did or did not get their degree in statistics, data-driven policy experts, government officials, all sorts of people. I mean that in the broadest sense. Okay. So in order to answer that question, the things we're going to touch on are broadly, what are the algorithms that we need? What's the tool case that we need, the tool set that we need to build out in order for the library to be of use to a large swath of practical analysts? In addition to that, not just what are the algorithms we need to implement, that we need to pull out of the theory literature and get into the library and polish and hone and get in perfect shape, but what are the algorithms that we need that the research community hasn't really fully addressed yet? Okay, so that's something that I think this group can help to create. Similarly, as we add in algorithms, what are the properties of those algorithms that we need to expose to the outside world, right? And what's the infrastructure for doing that well? So that's really what I'm going to focus on at first, and then I'll cycle back to the first two questions. So by that first one, when I say what's the properties we need to expose, okay, we know what differential privacy is. It's a definition of worst case privacy loss. Okay, it's very specific. It's a definition. Your algorithm meets it or it doesn't. Right? We know how to reason about cumulative privacy loss. This is the core sort of foundational thing here. But what we also understand is that the utility of those releases is the informational gain that the analyst gets from the thing that's been differentially privately released. And these things are at loggerheads. The definite, the foundational sort of work of Nassim and Danur is that surprisingly, or at least surprisingly 20 years ago, if you release things that look anonymous and they have informational gain, then they're going to be leaking privacy information. So how do we trade off between these two things? The first one, again, we can formally reason about, and we know definitions of exactly what the worst case privacy loss is for every algorithm that's being certified as differentially private. But it's often the case that for utility, we don't have as clear analytical solutions about what the utility of an algorithm is going to be in practice. Okay, this could be because utility is a strange concept, and it has lots and lots of dimensions, and to different analysts in different contexts trying to answer different questions, utility means lots of different things. So it's hard to reason about utility in a broad sense. It's also the case that it can be just generally harder to understand what utility is from an analytic perspective, even when you know what utility means in a particular context. And also utility can be heavily data dependent, right? So the size and the shape of the data, the distributions of the data, the strengths of the relationships, the prior information that already exists about some of these variables that help with your clipping bounds, all these things can be driving utility. So utility is extremely hard to reason about, but that doesn't mean we can just shrug, okay? It means that we need to make conscientious steps to make statements about utility so that analysts can understand what's going on in the data that's being released. And in two ways, and I'll differentiate this at the end, but I want to mark it up importantly at the beginning. Utility is important a priori and a posteriori. We need to be able to make statements about what we expect utility to be before the data is released, because otherwise analysts can't judge what workflow they should be spending their privacy budget on. And then a posteriori, after the release has been made, if those statistics are being used to reason or to infer about the outside world, they have to understand what the uncertainty of those releases are. And that's also a utility measurement. And that's something that Gary emphasized really importantly and heavily at the very, very beginning here. We need to have statements of utility and uncertainty for these things to be of use to statistical reasoners. Okay, so let me walk over this. And some of this is going to be bringing the computer science to the applied crowd, and some of this is going to be trying to explain sometimes to the theory crowd what it is that we, and I include myself in this we, as sort of quantitative analysts do with data. So let's say there's a population. This is the thing that exists in the wild. This is the set of all people, and here this is education values in the census. Okay, and there exists something I want to know about the population. It's very hard to see it, but this little blinking red line, that's the mean value of education. Okay, so we want to know what the mean population, the mean value is. I unfortunately don't have all of the world's data at my beck and call. I only have a sample of that data. I have the data that exists in my data set. Okay, it's often the case that when there are utility measures at all that exist in the literature, they're reasoning not about the utility compared to the population, but the utility compared to the sample value, sometimes called the regret. Okay. But one sample is no more valid than any other possible sample I might have generated. Okay, so I want to be able to reason not just about what my error and utility is going to be inside my sample, but what it is compared to the population or what it is compared to the next sample that I want to estimate. Okay, so let's say that I have a sample. What am I going to do? I'm going to compute a function on it that's differentially private. Okay, so here's the underlying function that I want to write, that I want to compute on this data set. That's the mean. There's my one mean. And let's say I use a Laplace mechanism. So instead of publishing this mean, or the mean from any of the other samples that I might have generated in the future, instead what I'm going to do is I'm going to draw noise from a Laplace distribution. And instead of publishing the red value, which is the true, and I say true in quotes, value in the sample data, I'm going to publish the green value, which is the differentially private value that I can compute using a certain budget from the sample data. Okay, so often what we do, with most algorithms is say that green line, if I tell you that number, that's going to be private. That's great. But it doesn't tell us much about what I can do with that number afterwards, how I can incorporate it into a statistical model, how I can guess ahead of time whether it's going to be close enough to the thing I care about, the red number or the population value, to know whether it's going to be of use. Okay, so what we need generally is some kind of, say after we've released that green line, the differentially private mean, some way of constructing an interval, perhaps a confidence interval, a credible interval, depending upon your system of inference, that says, yes, that green line is my best guess. No other value post-processed gives me a better answer, but I think the answer is somewhere in this region. It might be as low as 9.5 and it might be as high as 17, okay? Normally when we are able to release those things, they're really about the regret. That is the error compared to the sample, the function evaluated in the sample data. Okay, so so in this particular case, it happens to be that this confidence interval captures the red line. But as statisticians, and as Gary pointed out, that's generally not what we're interested in. And as so many statistical researchers have pointed out who have been using differentially private data somewhat in frustration and trying to communicate to this audience, what we're interested in is not reasoning about what their red line is, but reasoning again about this dashed red line, the true value in the population. And that's a different confidence interval. There's uncertainty, there's noise here, not just because Laplacian error was added to the red bar, but because that data that function was computed on in the first place was just a sample from the population, and that red bar had its own source of error. So how do we construct this blue confidence interval that says, not reasoning back to the data, but reasoning back to the population, what is it that I can infer? Okay, so those are two kinds of uncertainty. Uncertainty compared to the sample truth and to the population truth, both of which we need to expose. And it might be the case that we expose them in terms of intervals, or if we have a very sophisticated user, we might also want to expose a posterior distribution, a distribution that says, this is the probability of all the particular values could have been that would have resulted in the green differentially private answer that I got, okay? So here this blue line is the posterior distribution for where that red dashed line could be. And it's a conjugate of Gaussians and Laplacians, but it looks mostly Laplacian, okay? So revealing after the fact, both these red sources of uncertainty, the blue concepts of uncertainty that project back to populations or even posterior distributions are the kinds of things that make these releases more useful or useful at all to a statistical researcher, to a statistical reasoner, okay? If you are able to convey these things, if you're able to say, okay, here's a band in which that value might have been released, or here's the distribution that reflects my uncertainty about where that value actually is, then statisticians can take the numbers that have been differentially private released and go do their post-processing, which to them is, you know, the important work, right? The statistical model they want to run, and actually get back valid answers. So here's just an example of that at play. In the top here, we have a bivariate histogram that shows the relationship between education and income. And fortunately for most, as education goes up, income's going up reasonably high until you get to very high levels of education, and then it drops down a bit. You know, that's the story of our lives, probably. On the bottom is the differentially private version of that histogram, that bivariate histogram. So noise has been added. The same sort of pattern is there. If I look at it and I say, yeah, I know it's kind of noisy, I'd probably try and see the same relationship. If I just ran a correlation function on the top counts and the bottom counts, I'd get very, very different answers. Okay, so the red line here on the right is the true correlation in the top data. The purple line on the bottom is the distribution of answers, the distribution of correlations I would get from repeated simulations of this process. And what you see is this is what statisticians understand to be the case of measurement error. As you start to add error to the X's and to the Y's, which implicitly we're doing here, you attenuate relationships. Relationships seem less strong than they used to before. So the purple distribution centered at 0, saying there's no correlation here, when really the correlation is pretty strong. The correlation is about 0.28, okay? If I release not just the differentially private counts, but also the posterior distribution for all of those counts, I can put that into my model. I can build a maximum likelihood model that says, find me the correlation that best would have produced this differentially private graph, given I know the noise of all these estimates. And then we don't recover the truth with certainty, obviously. We don't get exactly back to that private answer, otherwise we'd be leaking information. But you can see the distribution of corrected correlations, the green distribution, is nicely centered on the true value. And if I'd used more epsilon, obviously that would have collapsed. So this is what we need to be able to do. We need to be able to provide to analysts measures of what our uncertainty is when we release differentially private mechanisms. We also need to be able to do this a priori and a posteriori. If the analysts themselves are constructing their workloads, they want to know before the thing has run what their uncertainty will be so that they can budget correctly and spend the privacy on the things they most care about. And then after the fact, they need to know what that distribution of error would have looked like from the cumulative algorithm so they can plug it into their models, okay? So I've used error here in that sort of graphical model as the underlying idea of utility, but to statisticians, there's so many different dimensions to utility. Utility is not just L1 or L2 error to some target, say the population mean. Different statisticians who are exploring different kinds of relationships or are making different assumptions about what their theory of inference is, that is how they reason from data to infer things they don't know, or have different objectives, have very different notions of different contexts in which utility changes. So sometimes I care about error, but if I'm doing a causal analysis about, say, whether a treatment regime is going to help or hurt a patient, I really care about bias, right? I don't want to get an answer that says something will not hurt my patient or will help my patient if my answers are biased. Sometimes I care more about variance than error. Maybe sometimes I care, and then there are these higher order ideas like invariance and consistency that are also desirable properties of estimators. And in certain contexts, they're really, really key. So there are a whole slew of things that are broadly called utility that statisticians might care about. From this understanding, these are 5 principles that are laid out in the section in the white paper on statistical functionality for the OpenDP library. There's 5 things that the library is going to need to accomplish in order for the releases that are generated from that library to be of use to applied analysts. And one is we should have a toolkit that has all the familiar tools that analysts need. You know, if they have methods of exploring data or methods of constructing models, we need to have analogs so they can do that in differentially private fashion. And that's something that the literature understands and has been picking up on. But also, we need to be able to explain what utility is going to mean before we run the analysis and after we've run the analysis for those kinds of algorithms. Everything that's in the library that's going to be of use to a statistician ought to come with some concept of utility, and it ought to be rounded out as much as it can. And where that can't be done analytically, which is often going to be the case, one way to achieve that might be through benchmarking, right? So the paper discusses or points, for example, to DP Bench, which was, you know, a pioneering way of doing this. Build up a corpus of analogous data sets, run algorithms across these data sets, and be able to give some a priori estimates of what utility will be across distributions of data sets and scales of data and other choices, epsilon choices. Okay, so building that natively into the platform is definitely something that I think is a core task. Now, people could disagree about any one of these, and I'm sure this list is not long enough. For the number 1 item here, which is what is the set of things that that analysts would need. We've been sort of polling colleagues and members of the DP design committee and some of the statisticians that we've have use case partnerships with already. And we got this sort of short list here of, you know, things that fall into 4 different branches of statistical, the statistical workflow. What do you do to curate data? How do you clean it and pre-process it before you run the model? How do you do exploratory data analysis to actually understand what the data is? And then finally, how do you run the model? These are kinds of things that people have said, these are the things I really would need in a library in order for my entire workflow to become privacy preserving. And it's clearly not long enough. Or it clearly might miss things that some of you as researchers have been generating that you think are really highly general purpose. So I would encourage you to, you know, speak out and say, you add to this list or point to your own work that you'd like to add to this list. One way to do that is there is this open document before the breakout session on Friday. And so at the bottom of that document, there's 2 things you could add. One, you could add questions if you think there's something that I've been talking about that isn't covered in your own work, or if there's something in the white paper you disagree with. Really, the goal here is to emphasize these points and try to coalesce a community of people who are doing research on algorithms, people who are doing translational work to build systems for users, and then those users and what they need in their use cases as statisticians and as analysts. How do we coalesce all those things together and come up with a statement that says, a library that is going to be useful for systems builders and analysts is going to have to emphasize and going to have these features and have, you know, as a minimum, this baseline functionality. So add your thoughts to this document, but also, you know, so that we all understand each other, because I think there's so much bridging work on this particular context. We're going to spend a fair amount of, Sasha and I are going to spend a fair amount of time on Friday allowing people to do lightning talks under these sort of different modalities so that we can all communicate with each other and understand, you know, what are the people who are working on statistically valid differential privacy, what are they doing? What are system builders seeing as the current holes in how libraries are used and adopted? And what do analysts really, really need that they're not seeing in the literature or in previous prototypes already? So by the end of today, please, if you're interested in giving one of these lightning talks, 1 slide, 4 minutes, very low key, it's just a way for us all to talk to each other. Do try and sign up on this Google Doc, okay? Thank you very much for your time. I think I've given myself 1 minute for questions if anybody has such a question.
Great, thank you, James. And sorry that you didn't get a proper introduction because of my technical difficulties and I fell offline. We don't have any questions specifically from your statistics talk, though audience members or participants are welcome to submit one quickly now. But one did come through on the programming framework that you may be a good person to comment on. Chinmay Shah asks, is there any reason for using Rust over C++?
Oh, absolutely. So I will give you a full answer about that in the next section, because I'm going to be picking up some stuff on systems integrations, and the language choice and the API choices are a big part of that discussion. But so as not to just seem like I'm dismissing the answer, the one sentence explanation that is a really good description of Rust is it's C++, except it's fixed, which is to say that it is very memory safe. And it doesn't have things like dangling pointers or memory races or all of the other sort of features that exist in C++ where you can't explicitly, concretely reason about how memory is going to be used. Okay, so it means that if we write code in Rust, it behaves and it performs a lot like C++ work, code does, but we can reason about it much more concretely, and it makes it much easier to prove characteristics of the code that you can't do in C++. So I'll talk about that more in the next section. And I'm happy to field more questions that follow on in that line.